Okay, number 3. So in number 3, you have a Ferris wheel with somebody on it, and that person is 70 kilograms. You're also told that the ride has an angular speed of 0.7 radians per second, and that variable is omega. The radius is 10 meters, and we want to find the force exerted by the seat on the person at a couple different spots. So you're looking for the force at the top, and then you're looking for the force at the bottom. Right, so the force of the seat at the top, that comes from a combination of different forces. So when the rider is sitting there, which is going to be that box, we're going to do a free body diagram, there's going to be a force upward. That's going to come from the seat pushing it up. There's going to be another force upward that is the result of the centripetal force. And then we have a force down, which is the force of gravity. When you set up an equation for this, that means that the centripetal force plus the force of the seat is equal to the force of gravity. So the question is, why is the centripetal force pointing upward? It's pointing upwards because technically when it pulls you down, the force felt from the seat on the person sitting there feels like it's being pushed upward. So that's why in the diagram it looks like that. So the sum of the upward equals the sum of the downward. And since we're solving for force of the seat, we can rearrange. You end up getting that the force of gravity minus centripetal is equal to the force of the seat. Force of gravity is mg. Force centripetal is mv squared divided by r. Both formulas have an m in them, so you can pull it out and end up with an equation that is mass times the quantity, gravity minus v squared divided by r. That's the force of the seat at the top. Now at this point we have most of the information. What we are missing though is the linear velocity. We know angular but not linear. We have an equation to relate them, and that's v is equal to omega times r. So we end up getting a linear velocity of 7 meters per second, which we can plug into the equation. If you wanted to, you could rearrange the original equation for omega, but I found that this is probably the easier way to do it. So you end up, when you plug in your values, 70 times the quantity, 10 minus 7 squared divided by 10, which is 70 times the quantity of 10 minus 4.9. You end up getting a value at the top of 357 newtons, which is less than the person weighs, which makes sense. If you've ever been on a roller coaster or something that's going over a loop at the top, you feel a little lighter than you do at the bottom or at any other point. Same is true if you're driving over a bump on the road, one of those hills. When you go over the top at a certain speed, you kind of leave your seat or you feel your stomach move. That's due to this type of relationship. So you end up with a force at the top that's small. So we go through the same process for the force of the seat at the bottom. So we're going to do the same diagram with essentially the same forces because you're doing a circle, so everything is the same. At the bottom, the force of gravity is still pulling down. And then at the top, you end up with the force of the seat supporting, and once again, the centripetal force is going to be pointing down because that's the way that it feels like it's being pushed. You feel like you're being pushed outward even though you're technically being pulled inward. So the force of the seat is equal to the sum of gravity and centripetal this time. So what you end up with is the same equations, all the same components, but at the top they are subtractive, at the bottom they're additive. So you get m times the quantity g plus v squared divided by r, which is 70 times the quantity 10 plus 7 squared divided by 10. So that ends up being 70 times the quantity 10 plus 4.9 instead of 70 times 10 minus 4.9. This force ends up being 1,043 newtons, which is really a lot, and it feels heavier than the person actually weighs. So the force of gravity should only be 700. So at the top, you are losing about 300 or so newtons. At the bottom, you're gaining those 300 newtons. So at the top, you feel lighter. At the bottom, you feel heavier, and that's by the same amount on both sides. So at the top, the seat is going to push up with 357, and then at the bottom, the seat is going to push up with 1,043. So technically, the weight of the person never changes, and the actual value for the force doesn't change, but the felt force by the seat is the thing that changes. So think about this conceptually. When you are on a Ferris wheel, they tend to move a little slower, so you don't totally feel this, but any ride that moves in a circle, where do you feel the heaviest? And the answer to that is always at the bottom, due to these calculations.